Alright, in this video we want to talk about two functions that you often see in more advanced tutorials, and that is XYZ dist and Primuv. Now you can use both by themselves if you want, but usually they come together because they kind of, work well together. Now the core idea is that you can find a specific position on the surface of an object by combining the UV information and the primitive number to find a very specific point on the surface that is unique. But I will explain this concept more clearly later on. Let's start simple. And let's start with what the XYZ dist is doing by default, is to find the closest position on another object surface and then calculate the distance. Now, if that sounds familiar to you, then you're right, because that's something we can already do. So if I have a point wrangle, and let's say for each point on this grid, I want to calculate the distance to the surface of the sphere here, I can use first minpos. So let's calculate, let's call it P2. And this is the closest position on the surface on the second input relative to my current position. We've done this before. Now, what I get with this is just where the closest position is. So let's calculate the distance from that, which is a float. And actually, no, let's put this into an attribute. And then we calculate the distance from this position we just found and our own position. And then we have the distance basically to the closest point on the surface of the sphere. So let's visualize this quickly. And there we have it. It's not amazing, but there it is. So the closer it is, obviously the lower the distance number will be. And then the further it goes away, the more it rises. Now this takes two lines of code or two functions. You can simplify this by using the XYZ dist. So if you want the distance to the closest point on the surface of another object, you use XYZ dist. And let's quickly look into the help because we've never worked with that thing. Here it is. And it looks like this. In its simplest form, it gives it back a float, which is the distance, and it needs a geometry, obviously, and the origin, which is just the position. So it's actually quite simple. It's just 1 and our current position. There you go, and we get the same result with way less code. So that's nice to know, first of all, that this is what XYZ dist is able to do for us. Now, the thing is though, if we look back into the help, there are more interesting things you can do with that. And that is if you add additional pointer variables, and we talked about this before, the small ampersand tells us, oh, we can actually fill those attributes here with data. And this is where the prim and UV come in. And the idea here is that you can not only find this point on the surface and its distance to the current point, you can also save where exactly that is in the UV space and what the primitive is. And the idea behind that is that this information is unique on the surface of an object. So let's quickly do this on another example to understand what this can be used for. And that is, for example, a sticky function. So let's say we have this sphere here, this surface, and we want to deform it with something. It doesn't matter, of course. So I took an animated mountain node just because, and I want to stick something to it. Now I have a problem. Sure, what I can do, and this problem actually can be solved in a relatively easy way for us already. We can just take a particular point and just stick an object to it like this little toy. And I know this is a bit of a simple example, but it explains the problem pretty well. So what we can do is we just take a particular point, whatever this would be, let's say point 12, I don't care. So there it is. Oh, that's a face currently. So let's select the point. There it is, this point. And we take our little toy here and copy it to this point with a copy to points. So what this will give us is that this toy here, there you go, will always be on the position of point 12, no matter what. So we can do with the sphere whatever we want, our toy will stick to it. This is fine and dandy, and if all I need is a position in space and I'm not very picky about it, then I can just take a point and that's it. But what do I do if I don't want to rely on a single point, but more like a proper position on the surface? So let's say there, over there. How can I define this position and this is important, find it again later on? And this is where XYZ dist comes in. because what we've seen, it takes two informations for us: the primitive of the position we found and the UV. And this is important to understand. There is actually no way to define this particular point on the surface on this object to find it later after it has been deformed by any kind of deformer. So someone came up with the idea of trying to figure out what kind of information does this point hold so that we can find it again. And the clever idea here was we just take the UV space. So if I press space 5, I'm in the UV space. And currently, as you can see, the sphere doesn't have any UVs. So let's do a simple UV unwrap, which is an automatic UV mapping. And important here, you have to do it before you deform it, of course. And if you look back at the 3D space, and actually let's look at both next to each other. There you go. The idea here is that if you look at the deformation in 3D space, you can see obviously my geometry is deforming constantly and changing its shape, obviously. But the UV space stays intact, and that's really the trick here. We can take the UV space information and from that find the position in space no matter how we deform the geometry. So for example, for now let's take a specific point because it's easier to show this way. This point in 3D space has the UV information, let's see, of roughly 0.8 and 0.2, and no matter where it is in space, this UV information will always be the same. So if I know where this position is in the UV space, I will always be able to find it in 3D as well by just converting basically the position to the 3D position, which actually the Primuv is doing. But why do we need more than just the UVs? Why do we need the primitive number as well then? Well, there is a problem with this technique. So let's maybe move this island here. So I switch to primitives and then UV connected geometry. And if I move this over here, let's say, I have a problem. And that is that the position in UV space for a specific point, let's turn this off again. Let's say this point on, again, something like 0.8 and 0.2 in UV space is not unique anymore. This point in UV space actually exists on two different faces. So to make this technique really bulletproof so that you can find a position on the surface, even if you have overlapping geometry, you can just combine the information of the UVs and the primitive number, which of course is the face number. And then you will always find an absolutely specific position in space by finding a specific position of a certain face and its UVs. And any position on the surface of this geometry here can be defined this way. So let's do this. We take the sphere again and the deformed version of it, and we have our toy here that I scaled down. And to find the position on the surface, let's move our toy to some specific position. So first of all, I use a transform for that, not the same that I used for the scale. And to make it easier, let's pack the whole thing so that we can handle our geometry as a single point. And there it is, just one point, and let's move it somewhere where we want to steal the position from. And maybe to make it more obvious, we can lower the resolution of our sphere to something like that. And I think we should now have a position that is in the middle of a face. So what we want to do is, before we deform the whole thing, we want to find this position on the surface of the sphere. And for this, of course, we use XYZ dist. And we actually want to find it relative to the sphere, so we do it this way around. And to do this, we need a primitive attribute and the UV attribute that we can write to. And the primitive attribute, of course, is an integer. So let's set this to -1. And the UV is a vector. So let's set this to, I don't know, 0, 0. It doesn't really matter. I take a vector here. We will only take the first two, of course, but it's the same as the vector information in the attributes. So with XYZ dist, we can actually not even take the output of the XYZ dist, but we can instantly just do the 1 and then the relative to the current position, and then we take the prim and the UV, because that's really what we care about. And what we should get now on the points is the information. Yeah, of course, we want to read this out as attributes so that we can actually debug this. So let's create a prim attribute where we write the attribute into the internal one, and UV vector where we write the internal variable to as well. So here we can see it. So the closest position on the surface of my sphere is on primitive 157, and the UVs are 0.3 and 0.23. So this will define the surface. So the question now is, and let's call this XYZ dist, what we do with this. Now we have the information, let's apply it. And this is where the Primuv comes in. So the Primuv function, if we look into the help again, takes the attribute primnum and UV and gives back, well, what? Well, any attribute we want for this specific position. So we can, read out, I don't know, the normals or whatever. But of course, what we care in this case is the position. So let's overwrite the position of our toy with P to the position from the second input. I want to use the mountain now, because what I want to get now is for the moving object, I want to get the position of this surface position that we just found with the help of the UV position and the primitive number. And this is in the second input, and the attribute we want to read out is the position. And we just take the prim attribute that we saved and the UV attribute that we saved, because that's the order the function expects. So actually, let's be more specific and use the right attribute data types. Remember, this is how we saved it. And now, as you can see, there you go. It finds the position thanks to, and I have some display error today. I don't know what it is. With the right lighting, it works though. There you go. With the information of where the toy originally was relative to the sphere here, we read out the UVs and the primitive where it was. And now with that information, we can read from the moving or deforming version, our mountain version of the sphere, where this position in space is when we give the Primuv function the primitive we're looking for and the UV we're looking for, and it will calculate for us any attribute we want, but in this case, the position. So as you can see, what you can use this for is to stick something to an object no matter where on the surface you want to stick it to, because this is a way to find that position in space no matter what you do with the geometry. So as you can see, it's a pretty complicated way of achieving something that with a little bit less precision you could also get by just copying something to a point that deforms with your object. But nonetheless, now we understand what the idea behind this is.